That's it. Okay, great. Welcome everybody to this special session of the Integral Systems seminar of BIMSA. So it's our great pleasure to have with us as a speaker from Jiangsu University, Professor Xia Limeng. So please go ahead. He will talk about GIM algebras and their modules.
Thanks, Pat, for your introduce and your invitation. It's my first time to make a talk in English. So my English is not good, and I'm very nervous. So
far so good. So far so good.
Yeah, okay. The topic of my talk is the GIM algebras and their modules. In this talk, mainly I introduce some background of the structure and the representation and the quantization and some knowledges about the generalized insertion matrix algebras. Then we introduce results on finite dimensional modules or indefinite type Kac-Moody Lie algebras. Okay. Let's begin by recording the definition of generalized intersection matrix. A matrix, a square matrix with integral areas is called GIM if the following three conditions are satisfied. So the diagonal numbers all are 2, and MIGI and MGI have the same signals, positive. Sorry. Sometimes MIGI is negative if and only if MGI is negative, and if it's positive if and only it's positive. So it's table. For the definition, one is referred to the two references. One is Slaughter, and another one is Bowman. Okay. Clearly, any GCM, yes, generalized Gaussian matrix is a GIM, a special one. However, GIM is not always a GCM. For example, let's see. This is a GIM, but not a GCM, because the number is positive. Okay. Let M be a GIM. The GIM algebra is a algebra generated by the three many elements similar to Kac-Moody Lie algebras, with subject to the generating relations. Yes, the first line and the second line defines the Kac-Moody Lie algebras, and the third line is the for GIM Lie algebras. So it's very case. So any Kac-Moody Lie algebra.
Sorry, is the only difference in the third line that you have the adjoint action of EI on FI?
EI and FI satisfy the cell relations, but not EI.
Nice. Okay.
Okay. Clearly, any Kac-Moody Lie algebra is also a GIM Lie algebra. Here, the special equivalent relation between the GIM. For example, fixing an index at 0, exchanging the positions of E at 0 and F at 0, and H at 0 take place in manner. Okay. So by using the new notations, the Lie algebra is generated by another GIM, but the Lie algebra is the same one. The matrix is a new one. So this builds a equivalent relation. similar to Kac-Moody Lie algebras, the GIM algebras also have linking diagrams. The unique difference is that if the MIG is positive, the length between I and J is the same case in minus MIG and minus MGI, but the solid lines are changed to be the dashed lines, or sometimes using the dotted lines. Yeah. For example, the linking diagram formation matrix is this one. So here, 1 and 3 between these the circles is a dashed line. It means that the number is 1, positive 1. Yeah. Okay. The corresponding GIM Lie algebra is not a Kac-Moody Lie algebra. In fact, it's a fixed point subalgebra, the affine Lie algebra of type A5. A5, yeah. Affine A5, yeah. So moreover, the following two diagrams are equivalent according this equivalent relation. Yeah. So roughly, an oriented GIM algebra is a GIM algebra, but it's not a Kac-Moody algebra. Yeah. So if GIM a GIM algebra is oriented, the matrix or the linking diagram must have a circle, and this circle has odd number many dashed edges. So, for example, this 1, this 3. Yeah. If we change the EIFI in one circle, the edges becomes another type. Okay. So any Kac-Moody Lie algebra is a GIM algebra, and any GIM algebra is a fixed point subalgebra of some larger Kac-Moody Lie algebra. This is the relation between these two type algebras. Okay. If L is a GIM Lie algebra, the context GIM algebra is a unit associated algebra generated to the elements EI, FI, and KI, and its inverse. We subject to the following generated relations. The relations R1, R2, and R3 defines the usual Kac-Moody quantum groups. Yeah. And this is a new relations, set relations for GIM type. I think Tan Price is the first one to study quantum GIM algebras. Tan Youjun, he's from Sichuan University. Yeah. Some other results here. It's another paper. And the S-Cube studied the GIM, sorry. His result is that the GIM algebra context GIM algebra is a co-address subalgebra of some quantum Kac-Moody algebra. So we don't know if there is a Hopper algebra structure on these context algebras. No. So Yun-Gao and Hu, my doctor supervisor, and I, they studied the context GIM algebras with simply list cases. Okay. Yun Gao and Nai Huanjing and I and Zhang Honglian. We studied untoroid quantum algebras and the extended context GIM algebra. There is this one, for example, N is 2 is Euro quantum toroidal algebras. It's a quotient algebra of 2 affine type context G algebras. In another paper, I consider the quantum toroidal algebras with parameter Q generic. This quantum algebras has no finite dimensional modules trivial. So this result is very different from the case of toroidal algebras. As we know, toroidal algebras has finite modules due to the affine case. Okay. But we know that if the context GIM algebra is the diagram is multi-affine type, the algebra has finite dimensional modules. It's different from quantum toroidal case. So the relation between quantum toroidal algebras and the extended context GIM algebras, we need degree operators, Q powers D. Yeah, so it's a special relation. Okay. Now let's return to GIM algebras. Our abstraction is a study is that they have no usual triangular decompositions. Yeah. So here are some references I know. In earliest, most works were done on IM algebras. IM algebras are some quotient algebras or GIM algebras. The corresponding matrix usually are diagonalizable, and so we can consider the length of the roots. So the IM algebras is a quotient so that the length of the roots is limited. For example, the longest one is the longest square length is 2. Yeah. In this paper, Heng and Xu, they introduced a class of quotient algebras. These algebras are some IM algebras. Yeah. They need the matrix is symmetrizable. So I and Hu studied another quotient. This class algebra and this class algebra has the same classification, but the algebras are not same. In this case, the square length of the roots can be very, very large. Yeah. So here is a realization of BCR type algebras. In this case, is also the IM algebra. Yeah. Okay. Recently, I and Yang studied the polynomial modules of some GIM algebras. For any n is larger or equal 3, a GIM algebra is of type ON if its Lie diagram is this case. So this Lie algebra is isomorphic to a fixed point subalgebra or the affine algebra, SL to N. So let G be of type On, and let H be the Euro-Gardner subalgebra of G. So in this paper, we classify all G modules V such that V is a rank 1 free UH module. This class module is a class non-weight modules in very many classes, Lie algebras or the super algebras and others. Yeah. For example, we solve Lie algebra. Yeah. Okay. For finite dimensional modules of GIM Lie algebras, I think the first one is we first consider a classes case. So for On, any finite dimensional vector space is simple module over On if and if it's a simple module over such algebra for some R. So it's A to N minus 1, Cn and Dn. Yeah. Color. We focus on finite dimensional representative theory for GIM algebras. Due to our knowledge, this perhaps is the first article to study the classification problem for this question. In fact, both in this article and in this article, all these two imply that the GIM algebra has non-trivial finite dimensional simple modules for any symmetrical semi-positive definite GIM. In this case, it has a quotient algebra is multi-affine or toroidal. Yeah. So toroidal Lie algebra has finite dimensional modules. So this is the result. Now, one has two problems for this case. To classify all finite dimensional simple modules over some given GIM Lie algebras, or to determine all GIMs so that the Lie algebra has non-trivial finite dimensional simple module. So there's two questions in this field. Yeah. We consider the GIM algebras with a thinking diagram of type Qn plus 1 AB. Yeah. This the On with Q. I and Liu studied this case. This case. That's N A is 2 and B is 1. So this T is a B2 type. Yeah, B2 type. So for N is larger or equal to 5, the Lie algebra has no non-trivial finite dimensional simple modules. It's a special one. If N is 3, oh sorry. Yeah, N is 3. So 3. Its module is equivalent to the white space as a module for this Lie algebra. C4, F4, and E6. Yeah. If N is 4, so the module is classified by the finite dimensional module over this algebra. Semi-simple. Yeah. This R and S and T can be any positive number. Yeah. Integers. Okay. In this article, we also studied the finite dimensional modules over GIM algebras of type theta to N plus 1. Sorry, P, not P. N is equal or larger than 3. So this one. This is a affine case, and plus this vertical. So if n is larger or equal to 5, so the Lie algebra has no non-trivial finite dimensional simple modules. Yeah. If n is 2, not 2. Yeah. So the third module is the default case. Yeah. Okay. Multi copy of default. If n is 3, it's due to the E6 type multi. And if n is 4, it's the E7 multi type. Yeah. In fact, we know that if we consider the Dinghy diagram is 1, 2, and this is a affine case. It has a fixed point subalgebra is of type ON. ON, yeah, it's okay. So this one is not fixed. This one is fixed vertical, and this one becomes a loss root. Okay, we obtain the Dinghy diagram. Yeah. Orient article is a partial result to determine the GIM algebras who have no non-trivial finite dimensional simple modules. Yeah. The main result is that any indecomposable indefinite Kac-Moody Lie algebra has no non-trivial finite dimensional modules. So, as a direct corollary, I know that any indecomposable GIM algebra containing an indefinite subalgebra has no non-trivial finite dimensional modules. So this is the meaning. Yeah. For example, if we consider Q n minus 1 AB, we may conclude that if AB, the product is larger or equal to 4, say it has no non-trivial finite dimensional modules. It starts to research the finite dimension module over the 3 cases, 1, 1, 1, 2, and 2, 1. And if the 1, 1 case for n is larger or equal to 10, it has no non-trivial finite dimension modules. In this case, for n is equal or larger 6, it has no. Yeah. In the following, we introduce the result. Any strictly hyperbolic Lie algebra G has no non-trivial finite dimensional simple module. A Dinghy diagram is of strictly hyperbolic type if and only if any of its sub-diagrams is a union of finite type diagram. No affine, no affine.
Sorry, can I double check? You have to also assume that it has to be not affine as a whole. Yeah, okay.
Yeah.
I see.
Okay. So hyperbolic algebra, Kac-Moody algebras were first classified with Dinghy diagrams by Limeng Lie in 1988. Those also were classified by this I don't know how to pronounce the name. Almost at the same time in this class. The classification result is also collected by Limeng Xia in his short book. Item for the 3 papers on several cases was listed by Lisa Carbon and co-authors. is 1. Okay. But this error term does not contain any strictly hyperbolic case. Here are the 4 references. Okay. The following is a unique series of rank 2 strictly hyperbolic case. A, B is larger than 4. Okay. Except this one, there are 35 many cases. I use a different notation from the other references. Okay. Here are the linking diagrams. And here, okay. 35. We first prove for rank 2 case. There's other outline the proof. We find a least algebra type A1, so such as we can find a highest weight vector, but the weight is not dominant. So if it's non-trivial, it has an infinite dimensional submodules for A1 type, for A1 subalgebra. So it has no non-trivial simple module. Okay. For the other cases, so the method is to find a subalgebra isomorphic to GAB. Yeah, for this case. So thanks. Thanks.
Thank you very much.
Okay, thank you.
Yeah.
So, I'm some nervous, so maybe I speak faster or not clear.
No, it was very clear. Thank you very much.
Okay.
Are there any questions or comments? Can I ask? You mentioned at the start that they arise as involutory subalgebras of certain Kac-Moody algebras. Which involutions do occur? I remember Kolb's paper is about involutions of the second kind. Is this the general
So
picture?
sorry, my listening is not good. So I need Chinese students translate for me. Okay. No Chinese students here.
Oh, I think there might be one. Maybe if you go back to one of the first slides about involutory subalgebras. Your first one of your first slides, maybe slide 5 or 6.
Sorry. Yeah. Is it PPT? No.
Yeah. But yes, if you go back to the start, I think you mentioned all.
Okay.
Yeah,
here?
you mentioned all GIM algebras are involutory subalgebras of Kac-Moody algebras.
Sorry.
Correct? The GIM algebras.
Yeah.
The GIM algebras are involutory subalgebras of Kac-Moody algebras.
Oh yes, This result. You can find the result in Burman's paper.
So can you explain which involutions? All involutions?
Oh yeah, it's a diagram automorphism and the Gaussian involution. The two composition. The composition of the two automorphisms. Yeah. So anyway, is 2 degree, and they are commutative. So it's still 2 degree.
So diagram.
Diagram.
And the other one?
Gaussian involution.
Gaussian involution. Okay.
Yeah. Okay.
So this is involutions of the second kind. So I think Kolb,
Yes,
you mentioned the paper by Kolb. Yeah. And okay, so I think he classifies these involutions of the second kind using Satake diagrams.
So the GIM algebras are classified completely. Yeah.
Yeah, but yeah. So is it the direct one-to-one relationship?
Yes.
Yeah, I see. Okay,
yes.
I see. Nice,
so Kac-Moody is GIM, and the GIM is subalgebra Kac-Moody. Yeah.
And so there's another extension of Kac-Moody algebras called Borchards or generalized Kac-Moody algebras.
Oh, I'm not familiar. I don't know that. I don't know that. I'm not familiar with that papers. Yeah.
I think it's similar because you also allow some weakenings on the entries in the matrix. So I think here the diagonal entries are allowed to be 0 or negative.
Okay.
For Borchards. Maybe there's some possible GIM generalization of Borchards. Okay. Are there any other questions? I've asked a lot of questions.
Okay. The quantum case is similar to the algebras. The quantum groups are contests the GIM algebras, and GIM algebras is a subalgebra of quantum groups, but it's not a Hopf algebra.
Yes. So is it always a co-ideal subalgebra of some larger? Always.
Yes.
Yeah, I see.
Yes.
Yeah. Okay. I see. Yeah. And so then you would probably expect so for the quantum groups you have the Hopf algebra structure and you have universal R matrix.
Yeah.
And so for these some of these co-ideal subalgebras you have also universal solutions of braid relations. Have you looked at this?
Oh no. Oh,
this is quite recent.
I introduced involution, but it's not on the field CQ. It's in that case Q is invariable. The parameter Q is an invariable, so Q should become to Q inverse. It's under the involution.
Okay.
So okay.
Are there any other questions? If not, let's thank our speaker again. And I think